Okay, so yeah, also from my side, welcome once more to this course. For me, it's a pleasure to be here, and I would like to give now a little bit more of a more basic introductory lecture than what we have just heard from Sue. So the purpose of my presentation is to introduce you to the basic concepts and principles of targeted and chromatography-based proteomics. So I assume that there are maybe people here in the audience that are already quite experienced in doing SRM or targeted proteomic experiments. But I think there are also a lot of newcomers, and so this lecture is especially for those people who are maybe not so experienced, and we will also have quite some repetition of things using slightly different words or different slides than what Sue said already. So I've structured this presentation into 4 parts. I would like to start with what is targeted proteomics, what's the definition of it, and why is it something useful to do, and Sue already gave some examples and some suggestions here. Then we will look a little bit more into detail how targeted mass spec data gets acquired, so what's really happening inside the mass spectrometer. And then I will speak also a little bit more about the prior knowledge that it's required to do targeted experiments, and in the end we will just look at some first real data. So if there are people here who haven't seen any targeted proteomic data yet or not worked with it, this is something to get familiar with it and to see what you will deal with through the next 2.5 days a lot in all these Skyline hands-on session. And whenever there are questions, please don't hesitate and interrupt me also at any time. So what is targeted proteomics? When I searched the literature for this slide to find a definition of what targeted proteomics is, it actually turned out really difficult for me to make this, because I think the term targeted proteomics is used by different groups on different continents and different backgrounds slightly different. So different people might include methods or technique into this term than others. So what I did in the end is I defined my own definition of targeted proteomics. So be aware, this is my view on it. And I think targeted proteomics is an umbrella term for all mass spectrometric methods that aim at accurately quantifying analytes for you that you already know that are interesting for your project. And these can be predefined proteins, peptides, or peptides carrying post-translational modifications. And in order to do such a targeted proteomic measurement, you unfortunately need to have some knowledge, prior knowledge to do that. So you must know how your analytes are behaving on your LC-MS instrument that you work with. So you must know how they behave during chromatography and how they behave in the mass spectrometer. Okay, so I told you, for me, targeted proteomics is an umbrella term, so there are various different techniques that fell under this umbrella term. And the 2 classical approaches that people use as targeted proteomic approaches are SRM, selected reaction monitoring, and PRM, parallel reaction monitoring. And what's special about these 2 data acquisition techniques is that here the data acquisition itself is already done in a targeted way. And we will soon look a lot more into detail how SRM works, but what you do with both of these approaches is you tell the mass spectrometer exactly about the masses of the peptides or the PTM peptides that you would like to monitor. And these are historically also, well, SRM is definitely historically the oldest and therefore also most established targeted proteomic technique. And also here in this course, you will work in the next 2.5 days mainly with SRM data. So all the data that you will look at is SRM data. But especially in the last years, also other data acquisition techniques have started to become part of this umbrella term. And these are the 2 other data acquisition types that are out there, which is data-dependent acquisition, shotgun proteomics, as well as data-independent acquisition. And what's special about these 2 additional data acquisition terms is that with these methods, the data acquisition itself is not done in a targeted way. So if we do a DDA experiment, we are not telling the instrument what are the interesting peptides for us. And the same is true in a DIA experiment. Here, the data is acquired untargeted, let's say, But there are new concepts, or there are strategies to analyze data that was acquired with DDA or with DIA in a targeted way. And if you use such a targeted data analysis concept, also these techniques might fall under this umbrella term of targeted proteomics. Okay, so what's unfortunately making this slide a little bit more complicated is the fact that for all these 4 different types of yeah? You're welcome. Yes, I'm not sure if they are on, probably, maybe they are not there already, but you will definitely get them. You are. So, oh, but maybe also as we know from you guys here, which type of data acquisition you have already used in your work. So who of you has already done SRM measurements and analyzed SRM data? Could you raise your hands? Okay, so like a third or almost half. Have some of you already done PRM measurements? Exactly the same people? Okay. DDA, shotgun proteomics, I assume almost everybody in here has done. Super. And DIA, do you have experience with DIA? Okay, also. So quite some experienced people here, I see. Okay, so what's a little bit complicating about this slide is that for these different technologies, there are also different nomenclatures around. So for example, SRM is also called multiple reaction monitoring, MRM. For PRM, you might also find the words MRM, high resolution, pseudo SRM or MRM. To do shotgun proteomics and use a targeted data analysis strategy. So the Skyline team calls it MS1 filtering. And for DIA, with a targeted or peptide-centric data analysis strategy, people use the word swath MS or hyperreaction monitoring. And there are even many more flavors of DIA. It's a very active research field at the moment, and they're coming out new approaches, new methods to acquire and to analyze DIA data. So the main reason for all these different names is mainly that different companies trademark specific names to their instruments. And then the rest of the world is not allowed to use this name anymore. So unfortunately, I think we will have to live with this problem that there are always different names that refer to exactly the same technology, just on different mass spectrometers. However, I think it's important that you're aware of these commonalities and these differences. Okay, cool. So why is targeted proteomics at all something useful? Why should we work with any of these 4 different types of targeted proteomics that I just showed you? And Sue already mentioned this also in her presentation. So the standard way, the data-dependent acquisition or discovery or shotgun or untargeted way of doing proteomics, which still definitely most of the people in the field of proteomics use on a daily basis, is a very valid and very important and very cool technique in the moment when you want to do identifications and in the moment when you want to globally map out which peptides and proteins are present in a sample. And it's also a technique that we can use to quantify. Everybody does that. But its major strength is to generate quantitative data matrices like the one here that contain a lot of proteins here on the y-axis. So with DDA, you can identify and then also quantify a lot of proteins. But what DDA is not so good in is to generate data matrices that have a lot of x-axis here, because and everybody who worked a little bit with DDA data knows this, I'm sure. The problem with DDA data is that you generate in these quantitative data matrices a lot of holes, a lot of missing values if you use DDA. And that's why these data matrices are quite sparse. And this often hampers nice quantitative analysis or statistical analysis of these large data sets. And in the light of this shortcoming, people started thinking about alternative ways to acquire the data, and that's when targeted proteomics came into play. Because with targeted proteomics, you can generate matrices that are more complete and have less missing values. So the axis can be much larger than DDA, while you still have very little missing values. However, if you work with techniques like SRM or PRM, so the number of proteins that you can put into this list is much more limited than in a DDA experiment. And with technologies like DIA, actually you try to combine these two worlds and try to generate quantitative data results that are both long on the protein list as well as lots of samples and a comprehensive, complete list. Okay? So better quantification, more consistent, more reproducible, more accurate quantification. That's the reason to do targeted proteomics. And the fact that this is really recognized in the field, you can see that targeted proteomics got selected as the method of the year by Nature Method in 2012. Now, so this benefit of better quantitation can be true for any of these 4 different data acquisition methods that I showed you. However, there are, of course, differences between these different data acquisition types. And I don't want to go into too much detail what these differences is and how all of these different methods work in detail. We will just focus on SRM in a second. But I would like to still give you a feeling of the differences of these different methods by using a very simplified but very nice and easy to understand analogy, which is the analogy of targeted proteomics to sightseeing Boston. Okay? So let's assume we want to do sightseeing in Boston. We want to take a lot of great pictures for our friends. And the DDA way of sightseeing Boston would be to take a look at intense peak, the highest building in Boston, and to first go to this building and take a picture and figure it out, assuming that this is a very important, very interesting building in Boston. And once you have taken pictures of this highest building, you would go to the second highest, to the third highest, and like this you would make your way down from the high level to the street level. Okay? What's very cool about this approach is that you will get, with this approach, quite likely, a nice overview over the whole city. And so it's quite likely that you will have high buildings everywhere. And of course, the more time you have, the further down you can go on street level. And that's the same in proteomics, DDA proteomics as well. What's not so cool is that your whole analysis will definitely be biased to the tall buildings. You will spend much more time on the tall buildings than on the street level stuff. And the quality of the pictures that you will make okay? So sightseeing Boston using SRM or PRM type of analysis, what would that mean? If you would use the SRM type of sightseeing, the first thing you would do before you travel to Boston, you would read the literature. So you would read the city guide book of Boston, and based on what you read there, you would decide what are the most interesting places to go for me personally. And then once you're in the city, you would just go to these places. And these places can be tall buildings or can be street level stuff. Can be a nice beer in a pub or a very tall building. It doesn't matter. It's not biased by the peak. It's just biased by your interest. So you can include the small street stuff much better here, but you do never get an overview over the whole city. You just go to certain places and don't get the big picture. And the quality of the pictures that you get because you spend so much time just on these specific places will be much higher than in DDA, and it will be also can be much higher for the street level stuff too. Okay? And the last way is to do DIA sightseeing in Boston, and that's definitely the most stressful way out of all, because DIA sightseeing Boston means going into Boston and photographing everything. So you would be these Google Street View people. You would just run around and try to, in this limited amount of time that you have, photograph everything. And you would just generate a digital map of Boston. And then once you're back home, you will start relax, sit down, and you would actually think about what have you photographed there. And you can, again, read the literature, find out what are interesting stuff to show off or to show your friends that you have seen that. And based on this literature information, you can zoom out of these many pictures the places that you are now are interesting for you. Okay, so you generate like a huge digital map of information of that place where you want to be. However, the quality of pictures that you took in this hurry of all these places is usually not as good as the quality of the pictures you can generate with SRM or PRM. Okay, Are there any questions? So I think this gives you an idea about the differences. And if you are interested in learning more also about PRM or DIA, which we will not cover in these 2.5 days so much, but please come in and see me to speak about the technical aspects of it. Okay, so second part of this presentation is about getting a little bit more nerdy on the mass spec side and looking at what's going on inside the mass spectrometer and how the data is acquired really in a targeted way. So here you see the standard workflow that is used in bottom-up proteomics. I'm sure you have all seen similar slides many times already before. This workflow includes that you always start with a sample that contains proteins from which you extract the proteins, digest them, and then you do at least one peptide separation HPLC step right online to your mass spectrometer. You ionize your eluting peptides, and up to this point here, it really doesn't matter at all whether you are planning to do an SRM, a PRM, a DDA or shotgun or DIA experiment. All these sample preparation considerations, SciLag labeling, yes, no, what Sue was talking about, this holds true for any type of these data acquisition methods that we already looked at. The difference really just starts at the latest step of this workflow, which is the mass spectrometry step. And if you want to do an SRM experiment, then the mass spectrometer of choice for you is a triple quadrupole mass spectrometer. And if you want to do a PRM, a DDA, or a DIA experiment, in our days, the most frequently used mass spectrometers for that are typically QTOF or QORBIs in the field of proteomics. So an SRM experiment can only be performed by definition will be the triple quadrupole mass spectrometer. And I will now mainly just look into this data acquisition on triple quads in SRM mode. So triple quadrupole mass spectrometer, as this name already suggests, in this mass spectrometer you have 3 quadrupole mass analyzers working in a row. The first and the third quadrupole, they both serve as mass filters. And the second quadrupole in the middle, this serves as the collision cell. So if now a mixture of peptides are co-eluting at the same time point from your LC system, this mixture of peptides, which is indicated here by these differently colored balls, will enter this first quadrupole, and ideally this first quadrupole will now isolate or select just a single ball out of this mixture of balls. So in my little toy example here, it would be the green ball that will be able to make it through the quadrupole. All the other balls will be filtered out to the sides. In an SRM experiment, you need to tell this first quadrupole exactly the M/Z value that you would like to pass this quadrupole. You need to have this information beforehand. Then this green ball, this precursor peptide, will be fragmented in the collision cell. And then in the third quadrupole, exactly the same process is happening as in the first quadrupole. So we will again select just a single out of these many different fragment ions that are formed here. And let just this single fragment ion pass the quadrupole, all others are filtered out. And then we will record the intensity of this single fragment ion with the detector. So, the unit or the thing that is always measured on triple quadrupoles in SRM mode are always pairs of precursor ion that's selected in the first quadrupole and the corresponding fragment ion which is selected in the third quadrupole. And there is a scientific expression for these Q1, Q3 pairs, which is called a transition. So a transition in the context of targeted proteomics is always a pair of a precursor and a corresponding fragment ion. And I will use this term now very frequently throughout the rest of the presentation. I think it will come up very frequently also in the next 2.5 days. And triple quadrupole mass spectrometers are able not just to measure a single transition in a measurement, but you can change these transitions rapidly. So in my little examples, I have, for example, selected 3 different fragment ions for this green ball. So 3 different transitions with always the same precursor mass, but different fragment ions selected here in the third quadrupole. Okay, and I think what's also very important to understand is that in SRM mode, at no point a full MS scan is recorded. So these full MS scans that we know from shotgun proteomics on MS1 or MS2 level, nothing like this is recorded in SRM mode. Instead, you really just always record the intensities of these pre-selected transitions, okay? But you do record these intensities continuously over the HPLC gradient that you apply, and that's why you can extract ion chromatograms from this type of data. So you can follow how the intensity of a certain transition rises and goes down again over your HPLC gradient, and you can use the peak area or the peak height of these chromatograms to do quantification, to do this type of analysis that Sue just explained. So what are the advantages of working with these triple quadruple mass spectrometers and doing SRM measurements? Now, triple quadruple mass spectrometers and SRM are very good in reducing noise because you have these two filtering steps. You do not just one filtering step as in DDA, but you do two filtering steps. And that's why noise can be quite efficiently filtered out. And quadruples are great mass analyzers in terms of transmission efficiency. So 95% of the green balls that actually enter this quadruple here will be able to make it through the quadruple. And these high transmission efficiency and the good reduction of noise are the reasons why SRM measurements are very sensitive. And as I already told you, you can tell the mass spectrometer on these transition lists, not just one transition, but you can put many transitions into such a list. And this is why you can do multiplexing, so you can measure several peptides, several transitions, several proteins. The disadvantage of triple quadruple mass spectrometers is their low resolution. So especially compared to the high mass accuracy, high resolution TOF or Orbitrap mass analyzers, this unit resolution of a quadruple is really poor. And that's why the selectivity of an SRM measurement on a quadruple can be potentially lower than the selectivity you can, for example, achieve in PRM mode on a QTOF or a Q-Orbitrap mass spectrometer. So there can be issues with selectivity in SRM. And the big disadvantage of target proteomics in general, you need to know what to look for in advance. You need to have these transition lists available, which we will look into more detail soon. And this transition list cannot be endlessly long, so you are limited in the number of lines that you can have in this list, which is in a routine way maybe in the range of tens to dozens to hundreds of peptides, what you can maximally target. Okay, I would like to have, to make this once more really clear, also for the beginners here in the audience, I have just one specific peptide example I would like to guide you through. So let's assume we would like to target this peptide here by SRM. You see indicated here the theoretical B and Y ion series. And if we want to target this peptide by SRM, what we need is such a transition list, or such an Excel table is it usually, where there are 4 columns absolutely essential for SRM. So you have the Q1 and the Q3 M over Z values. So these are the M over Z value you would like to isolate in the first quadruple, and the corresponding fragment ion you would like to isolate in the third quadruple. And in this example, these are the same precursor, and then Y5, Y7, Y8, Y10 as the 4 different fragment ions. And then there are 2 additional columns essential for every SRM experiment. One is the CE, the collision energy that you would like to apply in the collision cell. And I think also Sue has some hands-on data, right, where you will look a little bit more into these collision energies and how you can optimize them or how you can define them. And then there is the 4th column, which is called the dwell time. Sometimes people also call it the accumulation time or the acquisition time. And that's the time that you would like to provide the mass spectrometer to accumulate signal intensity for a certain transition. And usually the more time you give the instrument to accumulate signal, the better it will be able to differentiate a true signal from the noise. Okay? Ideally, you would like to have nice and long dwell times, and you can be very sensitive in your measurements. So if you copy-paste such a table into the acquisition method of an SRM instrument, and if you press the start button, what the instrument will do, it will go to the first line, to the first transition, it will set Q1 and Q3 according to these values, and then it will just accumulate the signal intensity of this transition for 250 milliseconds, and it will record an intensity value that it saw. After 250 milliseconds, it will switch to the second transition, change the settings of Q1 and Q3 accordingly, and record the intensity of that transition. And like this, the instrument will cycle once through the whole list that you provide here. And once it reaches the end of this list, it will simply jump back to the top and do this cycling through the transition list over and over and over again, over the whole gradient that you apply. And if you're lucky, then your data that will come out will look like this. Yeah?
So if you have a peptide that is, you know that the abundance is very low, and you want to have a greater accumulation of dwelling time, could you have different dwelling times?
Exactly. This is definitely possible for, I think, all mass spectrometers vendors. You can use different dwell times for different transitions. You can use different collision energies. You could, in theory, even have, usually you do this on precursor level, but you could even use different values for different transitions. Yeah, and it can make a lot of sense, even though it also means even more upfront optimization work if you want to optimize all of that. Okay, so if you're lucky and if you acquire the data for such a list, you will get these extracted chromatograms from a skyline picture here that look like this. So you see here the intensity of these 4 different transitions indicated in the 4 different colors going up and down. And what's very important to immediately recognize about these chromatographic show exactly the same chromatography in terms of peak apex and peak shape. Okay, and this is a very important first prerequisite in targeted proteomics. If you look at different fragment ions from the same peptide on the column during chromatography, this was just one molecule, right? So different fragments should show exactly the same chromatography. They have different intensities. Right? So different fragment ions can show different intensities. This is in analogy to that different fragments in an MS2 scan that you are known from DDA work have different intensities just depending on the fragmentation properties of a peptide. Now these almost smooth lines that you see here is not really what the mass spectrometer recorded, right? So this is already the extrapolated peak, more or less, from the software. What the mass spectrometer really records, as I just showed you, are distinct intensities at distinct time points. And the time difference between 2 of these neighboring points is a very important parameter in targeted proteomics, well, in any type of proteomics, and it's what people call the cycle time. And in SRM, the cycle time, so the time between any of these 2 of these neighboring points, is more or less the sum of all the dwell times of the transitions, because that's the time that the instrument will need to once cycle through this list and before it can jump back to the top and do the recording of the same transition again. Okay, so in this toy example, I have 4 transitions with 250 milliseconds. So the cycle time, the time difference between the recorded time points will be roughly 1 second. And if you now, with this, keeping this in mind, I think it also becomes very clear that if you want to do good quantitation, if you want to extrapolate a true peak shape, it is very important that you sample an elution profile of a peptide frequently enough so that the software can really extrapolate the true peak shape. And the rule of thumb, what people try to work with, is to use a method that provides you roughly at least 10 data points over the elution profile, because then a software algorithm can more or less nicely extrapolate the peak shape. And this is shown here. Once more for different peak width, because what gives you now 10 data points over the elution profile will strongly depend on the width of your peak. On nano LCD systems, very often peaks have peak width in the range of maybe 30 seconds. So if you consider a peak width at base of 30 seconds. A cycle time of 3 seconds would give you 10 data points over the elution profile. If you have a very good performing LC system with very sharp and very narrow peaks, a time of 0.5 seconds is necessary in order to give you 8 data points over the elution profile. So the point I want to make with this figure here is that if you think about targeted proteomics, actually if you think about any type of quantitative proteomics, because this is equally true for also shotgun proteomics and MS1-based quantification, you always must make sure that your cycle time is in accordance to your average peak width on your specific LC setup. Yeah?
I don't know, has it been implemented by now as a requirement for application, or is it still kind of a suggestion?
You mean into the acquisition software that it automatically recognizes that, or?
Like for MCP, you need to report how many data points you have if you have quantitative proteomics, because people talk about this a lot. Is it really a rule by now?
I don't think this is a rule by now. And of course, a little bit of a problematic thing is that the peak width in a measurement is not set in stone, right? So there can be different peak width within one measurement, depending on the concentration of the peptide and so on and so forth. So usually people try to work with the average peak width, that this should be according to 10 data points. But I'm not aware of any rule in publication process, you mean, where people prove that. I don't know, in the back line, if you're aware of something like this. I doubt it. You could suggest something like this to MCP. Okay, so in order to wrap this up once more, SRM targeted, you generate a transition list to do an SRM experiment. There's always a balance of 3 parameters that you need to make. You need to balance your dwell time, your cycle time, and the number of lines that you can have in this transition list. And what you want to achieve is, of course, you want to be really sensitive, you want to be accurate, and you want to have not just one protein on your list, but several. And in order to achieve all of these things, to be really, you need rather long dwell time. In the SRM, we'll typically work with is dwell times in that range. So 5 milliseconds being not so sensitive, 200 milliseconds being very sensitive. Cycle times, in order to reconstruct the peak shape, you need 10 data points. So depending on your LC system, these are often cycle times in the range between 1 and 3 seconds, maybe 4 seconds, also depending on the gradient length that you apply. And number of transition experience I could always perform rather, let's say, routinely without a lot of optimization is maybe in the range of 1,000 transitions. With newer instrumentation, of course, the faster the mass spectrometers get, the bigger this number gets. But 1,000 transition is definitely already something quite challenging. And also 1,000 transitions can only be achieved, and Sue brought this up already, with something that is called retention time scheduling. So what means retention time scheduling? What you do here is you do not acquire the transitions in your transition list over the whole HPLC gradient that you apply, but you put your HPLC gradient into certain segments where you expect your peptides to elute. So if you already know peptide 1 is eluting at 12 minutes, you will just acquire the transitions of this peptide from 8 to 18 minutes, for example. And then peptide 2 elutes at 25 minutes, so you will put in the second segment just the transitions of this peptide 2. This retention time scheduling is really cool because it helps you to increase the number of measurable transitions in one run. So you can put not just 100 or 200 transitions, but 1,000. It can also help you to improve dwell time and cycle time. Give longer dwell times to certain transitions, make your cycle time faster. But in order to do exactly this type of retention time scheduling, you need to know where your peptides elute. And they need to elute there reproducibly. Because if you're acquiring the transitions in the wrong window, the data is lost or not useful. And that is a big problem because retention time is actually something that is LC platform, gradient length, column age, sample metrics dependent. So if I tell you I measured a peptide with SRM that it was eluting at 16.3 minutes and you want to do it in your lab, this is completely useless for you, this information. And that's why it is super important to somehow, if you want to use this scheduling and chromatographic information, to somehow standardize retention time information. And that's what was also already mentioned by Sue a few times, is what people achieve the standardization of retention time information by storing retention time information not in the unit minutes on my system, but they rather make retention relative to a set of reference peptides. And as long as we work with the same reference peptides, we can immediately correlate and calculate retention time between systems. And yeah, this is also what we will refer to the IRT concept. And there will be a whole hands-on session and a whole lecture for you given by Lindsay, who will explain you all of that in detail and how it works in Skyline. Okay, so to wrap this up, performance profile of SRM. So SRM is an ideal technique if you want to monitor a rather small set of predefined target proteins or target peptides or target PTMs, and if you want to do this reproducibly over many samples. If this is the task of your project, if this is what you need, SRM can be a very attractive method for you. A cool advantage of SRM is its very wide dynamic range. So SRM and PRM can cover the widest dynamic quantification range, 4 to 5 orders of magnitude. It's high reproducibility and repeatability, and also SRM is very well supported with software tools like Skyline and spectral repositories. You can actually get a really good start, a quick start into it. Disadvantages: you need to have prior knowledge about all your target proteins and PTMs. It's what I refer to as peptide query parameters. So you need to have a ready assay. The resolution of the triple quad mass spectrometer is rather low. And this can be problematic, especially if you're interested in really quantifying accurately peptides that have a very, very similar mass. So if they are nearly isobaric peptides, and it's for you super important to differentiate a certain modification that is very isobaric from each other, then SRM might not be suited, and maybe with a PRM experiment where you have the higher resolution of an ORBI or a TOF mass analyzer can be more suited. And you are limited in capacity, so roughly 1,000 transitions per run, what you can achieve easily and routinely. Are there any more questions how SRM works? What the mass spectrometer does in an SRM measurement? Cool. So then let's look at how this prior knowledge is generated to do exactly such an SRM experiment, or the knowledge is actually also needed to do a PRM or a DIA targeted analysis as well. So I already told you what you need are these peptide query parameters, and peptide query parameters are nothing than a list or a big table with information. So this is typically the format how these peptide query parameters are gathered, or what are the important columns. And it's very similar to this table that I just showed you before for our little toy peptide example. So peptide query parameters is a table where you have the protein name, where you have for this protein the best peptides, whatever that means, that you would like to target. Then you have here all the mass spectrometric behavior, the Q1, the Q3, charge state information, ion type, and also fragment ion intensity. So this is an important column also where people store the information, what will be the most intense fragment ion with 100%, the second most, the third most. And this is a type of information that you do not need to acquire SRM data. The triple quad doesn't care what's the most intense or the second most intense one, but this is very useful information that you need to analyze the data afterwards in order to confirm the identity of the peaks that you have found. Then there is this column called normalized peptide retention time. So this is here these IRT values, these retention time information relative to a set of reference peptides, and also the collision energy information is needed if you do SRM. So that's these typical peptide query parameters that you need to generate upfront or that you can potentially download from the internet. And this peptide query parameter, no matter whether you want to do an SRM, a PRM, or a DIA experiment, is needed for all of them. For DIA, if you want to do a targeted peptide-centric data analysis, you would also use exactly such a table. So how do you fill the table? Where does all this information come from? And there are two different approaches how you can fill this table with all this information. The one approach is to go purely theoretical. So there are prediction tools for everything that is in that table. There are tools all these tools are already rather old. There are also currently still a lot of research ongoing, theoretical prediction area. You can predict what protein sequence, the possibly best peptides of that protein. You can predict the fragmentation pattern of these peptides, and you can also predict retention time information simply based on peptide sequence. However, the theoretical predictions, how they worked, at least in the past, were never as accurate and as well working than relying on some real empirical data. And that's why most people always start building assays from empirical data, just because it's very hard to predict everything as nicely. But who knows? So there are still lots of progression ongoing, and maybe at one point we are able to predict everything, and then nobody would care about empirical data anymore, I think. So, but if you rely on empirical data, what people try to do is they try to select the 3 to N, 4, 5, 6. I mean, I would always say the more peptides you can target for a protein, the better. And they try to select the most intense, at the same time unique peptides per protein. And the scientific expression that was coined in the field for these most intense and unique was proteotypic peptides. So a proteotypic peptide should be a peptide that is high intense in the mass spec and that's unique for a protein. However, especially in 2011, for the first time, also the term quantotypic peptides came up. Has anyone of you heard about a quantotypic peptide before? This term? Yeah? What's a quantotypic peptide? A peptide for quantification? Yeah? But what does it mean? I mean, proteotypic peptides are also peptides for quantification. Yeah? Loud?
It's probably sequence dependent. So
Mhm.
have new fragments, I would have anything like methionine that would be oxidized.
Yes. Yes. Very good. So quantotypic peptides, what the people from this authorship here, from this paper wanted to say with this term is that these are peptides that should be ideally suited for quantification. And that means a quantotypic peptide should fulfill quite a few more rules or features than just being the most intense and being unique for a protein. And I've tried to summarize some of these rules here on this slide for you. So for example, people also try to work with peptides that are completely digested by trypsin from the mother protein, or by any protease, if you like, by the protease you work with. If you work with trypsin, it's, for example, people try to not work with peptides that are not fully cleaved, right, that still contain a lysine or arginine somewhere in the middle. Peptides that have these rect ends here are known to be cleaved less optimal by trypsin, so try to avoid those. Peptides that have acidic residues close to the cleavage site are often not cleaved 100%, so you can try to avoid those as well. KP-RP is usually considered as being not cleaved by trypsin, but actually it has been shown that it does sometimes cleave. So you can, in order to avoid problems with this, you can also try to avoid these sequences in your peptides and avoid peptides that just have slow or strange digestion kinetics, right? If you look at how peptides are digested over time, you can observe very strange effects of peptides that are peaking and degrading again, or very slowly digested. Ideally, you would like to work with peptides that are formed quickly by trypsin and are then stable over time. Stability over time again, so there are peptides who are not stable at 4 degrees or room temperature for several days, and then they're of course poor analogs for a protein concentration, or that are not stable when you freeze and thaw your samples. Ideally, a quantotypic peptide should be also a peptide that is not prone to chemical modifications. That's what we just heard. You don't want to have oxidation of methionines or tryptophan. NG, QG can be prone to deamidation, or cyclization of N-terminal Q and E can happen. And then there is also the biological PTM. So if you want to quantify the concentration of a protein based on peptides that are representing this protein, peptides that carry a biological PTM are not that well suited, because very often this biological PTM is not there to 100%, right? Just a certain fraction of a protein might be modified. And how can you try to avoid these PTM carrying peptides? Well, you can check repositories for PTM. You can avoid known motifs, like the NXST is a known glycosylation motif. You can try to avoid that. Or you can try to avoid the very N or very C-terminal peptides, that they are often signal sequences and therefore also cleaved off. Now, these are all rules that you could apply to find the very best suited peptides for your protein in the context of quantification. And all of these rules are valid, and all of these rules are good to follow, because they likely help you to do a better quantitative measurement. But if you follow those rules, in many cases you will end up with a single peptide that meets all of these criteria for a protein. And that's why not everybody applies all of these rules, simply because it's not possible. And just my last comment to that is that I think especially these first three criteria here, stability over time, complete proteolysis, chemical modifications, is something that, as long as you're just trying to do relative quantification between samples, and as long as you somehow make sure that incomplete proteolysis is done reproducibly for all the samples that you compare, your quantitative result can still be correct. However, if the purpose of you is to do absolute quantification, so if you really want to determine the concentration of a protein in the sample, each of these effects will immediately influence your absolute quantitative results. So then it becomes, if you plan to do absolute quantification, these rules become much more important for you compared to if you just do a relative quantification between a lot of samples, but you must make sure that these things are happening in a reproducible way to everything that you relatively compare. But it might make you feel a little bit better on relaxing on a lot of these rules. Okay? Okay. Good, so peptide fragments, 4 to 6 most intense and unique peptide fragments, and retention time normalization using IRT means using empirical data to gather information about where certain peptides are eluting from your LC system. And all of those empirical parameters can be derived from what we call spectral libraries. Okay, so what's a spectral library? Yeah?
About the fragments.
Yeah.
If you put all the effort to select the peptides ideally, wouldn't it be also possible to go down with the amount of fragments per peptides to improve multiplexing capacity?
Yes, you can go down or right. You also work isotope labeled. Whatever type of isotope labeling, you will go up with the number of transitions. Again, just everything goes by 2 if you look at several channels. So it's really a trade-off of things that you can do. That's also why there are 3-2 something, 4-2 something. It's a balance that you need to find for your project. Yeah. Exactly. So what's a spectral library? So all these parameters, if you want to fill your peptide query parameter table from empirical data, a good way how to do that is to take a spectral library. And the spectral library is nothing else than high quality MS2 spectra, from which a certain peptide sequence was identified with high confidence. So a spectral library is just a compendium of identified peptides and their corresponding MS2 spectra, okay? And usually spectral libraries are built from DDA measurements, okay? And ideally you try to build a library from high quality DDA measurements. And then this whole table, which I just showed you and where we went through all the columns, all the information to fill these columns is stored within such a spectral library. So which peptides were identified, with which fragment ions, what is the relative intensity, peptides spiked in and analyzed in this spectral library. You can also generate this normal from there. The question is now, which samples can you use to generate such a spectral library? And what most people do is they work exactly with their samples of interest. So where you also want to do an SRM experiment on later on, these are the samples you will first measure by DDA, generate a spectral library, and use the information from the library to query, generate these peptide assay parameters, peptide query parameters, which you then acquire in SRM mode, or use for peptide-centric analysis in DIA if you have acquired your data in DIA. The problem with this approach is that if you just work exactly with the samples of interest, the sensitivity here will be limited by the sensitivity of a DDA experiment. You will just be able to detect stuff in SRM that has been detected before by DDA. And that's why very often people do, for this purpose of spectral library building, an additional peptide sample fractionation step, just in order to increase a little bit the depth with which they can dive into the proteome and to generate a larger spectral library. But other approaches that are also very valid for spectral library generation is to work with synthetic peptides. So if you can order a lot of crude synthetic peptides, you will generate quite likely very high quality MS2 spectra that then can be used in your library, or full-length recombinant proteins that the McCoss group does a lot. So express your target proteins recombinantly, and this will also generate you very high concentrated peptides, very nicely high quality MS2 spectra. And the last option is to not do any of these measurements yourself, but simply look what's out there in the literature and try to find public libraries that you can use as a starting point for your own experiments. And here on this next few slides, I would just like to give you a glimpse on that. Everything that I showed you now is something that Skyline really supports and makes really easy for you. And you will do this in these hands-on sessions very soon. So in Skyline, there is something that is called peptide settings, and there you have a library tab. And here you can actually either load or even build from raw mass spec data and from database search results. You can build libraries within Skyline, and then you can tell Skyline that you would automatically like to pick certain peptides from these libraries and do a ranking of how many peptides you pick, like 6 peptides based on their picked intensity. So once you have a library in Skyline, Skyline does all this automatic selection of peptides for you automatically, and you will learn how to do that. Also, automatically selecting transitions is very easy. There is a transition settings tab, and again, a library sub-tab here where you can tell if a library that I've loaded in Skyline is available, pick me the 6 most intense product. And you can define here in some other filters whether you just want to look at Y ions or just B ions or both. And you will also learn how to do that soon. And the last thing, retention time. So again, in peptide settings, there is this prediction tab that allows you to generate a retention time predictor. And that's also what you will do in the afternoon. And then you can use Skyline to automatically generate for you IRT values, which are normalized retention time values. And this slide is just once more a summary of what Sue already shows you. So if you decide to also work with public data people, there are a lot like SRM Atlas, WOF Atlas, Peptide Atlas. This is all from the ISB team. From then we have this assay cancer from the NCI, this repository which Sue showed already. Panorama from the Skyline team. Proteome Tools is a database from Munich. Cost Group has this passport website. So there are a lot of repositories out there, and I can just highly recommend you that you should check those repositories before you start generating own assays, because it can save you a lot of time. Any more questions on how the prior knowledge is generated? What's a peptide assay peptide query parameters. Yeah. Mm-hmm. Mm-hmm. Well, the Y ions for SRM ions. On our Q12s or Q orbis, and the fragmentation mode is quite a bit different, even though if you use HCD mode, but still people have seen that the Y ions are more conserved than the B ions. That's a major reason that I'm aware of why people like to work with Y ions. However, in the moment, if you are, for example, generating a spectral library on exactly the same instrument type, or even exactly the same instrument in your lab, where you will do targeted assays, then you can really assume that the fragmentation pattern will be exactly the same. And then I would just include whatever is in there. It's mainly when you shift between instruments there was a reason to use the Y ions. I never thought, I never did that before. Maybe there are some cancer people. Maybe I assume this is a question that will come up very often. My feeling is I remember that with this, but this is very specific now, so maybe this is not super interesting for everybody. We should definitely do that a bit more, but my feeling of when I was involved a little bit in something like this is that actually it is quite unlikely, or it's very rare that you see exactly the mutated peptide also then later in the data. So even when you went through the hassle of trying to include all of them, the benefit was minor because you could hardly detect any of them anyway. Let's make a discussion round once more offline. There will be a lot of time to about these things. My short answer is I think very often, yeah, it was not very successful, or you need to put a lot of more upfront work to know exactly which is detectable and what do you want to follow up. And it's not like a global screen that you will do with targeted proteomics. Okay, super cool, but it's great that you're asking so many questions. Are there more questions? Cool, then the last part is just looking with you at some real data so that you get a better feeling of how SRM data looks like, because you will look at it in the next 2.5 days a lot. And if you load SRM data or PRM data or DIA data into Skyline, they will all look the same. So that's the first good news. Everything looks the same. If you want to judge quality or identification of a peak that Skyline picks for you, there are 6 criteria that you can apply or that you can investigate and look at when you are looking at SRM data. And the first criteria I already told you when I showed you this first little toy example is co-elution of transitions. So if you see a peak like this in Skyline, so in Skyline will almost always, very often pick for you peaks that you load into Skyline, and it will always show you which peak it has picked by putting this triangle on the apex of the most intense transition, and it will always show you the peak boundaries with these dashed lines here, left and right. And if you see a case like this one here, where you have 3 transitions that are where the peak apex is very similar, so we will call they are co-eluting, this blue transition is clearly different. Their peak apex is somewhere else, which means that this blue transition is not coming from the same peptide than the other 3. Okay, so that's the transition that you would ideally need to exclude if you want to quantify that peptide, because it's not coming from the same peptide. So if you are having interference-free nice transitions from the same peptide, they should all be co-eluting. Another criterion that you can check is peak shape. The same reasoning. If you have transitions coming from the same peptide, they should all have the same peak shape. And if you have these strange peak shapes like here, so not a nicely Gaussian peak shape, but some weird stuff, and more confident that they are all coming from the same peptide precursor. And then there is a third criterion which you need to be a little bit careful about, and this is signal intensity. Transitions of a that were coming from an optimized assay it's quite likely that they should also give a highly intense peak. So if you see, like here, there are 2 peak groups where all of those transitions are co-eluting. It is, let's say, more likely that it's the most intense of these peak groups, but this is not at all set in stone, right? So if you have an interfering peptide that has a very high concentration in the sample, it might well be that this is coming from the interfering peptide and this is your right peak. But signal intensity together with other criteria to check your peaks is something you can also consider. Okay, so these 3 criterion here, you can always apply immediately when you look at chromatographic SRM data. You do not need to have any prior additional knowledge. You just look at the peak and you look, is it co-eluting, has it in peak shape, is it nice and intense? But unfortunately, for a lot of files or for a lot of complex samples, using just these 3 things to check is not enough to be really confident that you are measuring the right thing. And that's why it's important to have additional knowledge or additional parameters that you can check. And one parameter is correlation to the library spectrum. So if you have a spectral library loaded in, if you have an MS2 scan from which a certain peptide was identified, you can check whether the intensities in this MS2 scan of the fragment ions are matching the intensities of your chromatographic traces. And Skyline makes you this correlation between the traces and the spectral library really easy because it will compute for you a dot P, a dot product, which is just a mathematical correlation. It will be always between 0 and 1. 1 means perfect match between these intensities. 0 means no match. So you can quickly check by looking at dot P values in Skyline if the intensities that you measure match the library that you loaded in Skyline. Yeah?
So one number is a good match, but it's not.
1 is and 0 is not matching at all. So now you are asking, is there a hardcore cutoff that I can apply that everything that has a dot P higher than 0.9 is always my correct type? And the answer, unfortunately, is no. It's not so easy to give any of these hardcore cutoffs, and I would even not recommend you using a hardcore dot P value cutoff, because the problem is that the again, speaking about a case where we have acquired a library on a different instrument, when we did a Q-Orbi measurement, DDA measurement, and now we are measuring on an SRM TSQ Vantage instrument, you can't expect to have a similar good dot P value. Keep a little bit in mind, where does this library come from? Is it really from me, from the same instrument? Then I would expect you should get very good dot P values. If it's a library taken from the internet, measured on a different instrument, the values will be much poorer. So there is not a hardcore cutoff value to work with. And I can really just say you should use this criterion with combination with the other 6 that I show you here. It's just one piece in the puzzle. Because there are sometimes cases when you have maybe a dot P of only 0.8 or 0.7, and still it's the correct peptide. But for some reason, maybe there was an interference in the library generation process, and it just doesn't match so well. Okay, the 5th criterion you can look at is correlation with retention time. So if you have retention time information, IRT values predicts a certain peptide to elute in your run, and you can check, is this close to where it was predicted, or am I far away from that? That will also help you to sometimes guide identifications. And the last criterion you can use in SRM is if you have heavy labeled reference peptides, protein standards spiked in, and if you measure light and heavy chromatograms, you can check whether these light and heavy are co-eluting, have the same relative intensities, and there is also a dot P that Skyline calculates for you between light and heavy peaks. It's not dot P, it's R dot P, and this will also be between 0 and 1. 1 means that the relative intensities of the light peak and the heavy peak are perfectly matching. And this, for example, is a dot P value that should always be very, very high, because you measure the light and heavy in the same experiment. So you should really just see R dot P's of 1 or 0.99 Cool. So now I have just prepared. I made this new slide of. So these are these 6 criteria you can apply to SRM data, but there are a few more parameters or more criteria you can apply to PRM or DIA data. Any one of you, and you shouldn't look into your slides now. Who has? Oh no, but you don't have my slides yet, right? Very good. So yeah, I will put them later. That's very good. So. No, not yet, not yet. First, I want to have from you. So what are additional information that you might find in PRM or DIA data, which is not available in SRM data, and that you could also use to check, score the peaks that Skyline has picked for you, yeah? Acquired on high resolution, high mass accuracy instruments. So you have mass accuracy for your fragment ions, and you can check for that. Exactly. That's one parameter you can apply, look for mass accuracy, ppm error in when you have other type of data. Other information that is in PRM and DIA data and not in SRM data. Yeah?
Maybe your precursor area on a
Super, exactly. That's already all I wanted from you guys. Exactly. So in PRM and DIA data, you usually have an MS1 scan included. So I can just highly, you do not necessarily need to do this, but most people do it, and I can only just highly recommend you. You should include a full MS1 scan in your cycle, and then you can exploit all these MS1 scan information. Exactly. So this is just shown here. Oh, and there is one more I forgot about. So you have high mass accuracy, high resolution MS2 data in PRM and DIA. That's why you can look at mass accuracy, product mass accuracy. Another type of information that comes with it is that you can look at the different isotopes, monoisotopic, first and second isotope, which is also something that you cannot do with SRM data. And what Skyline then will do for you is, based on the peptide sequence that it expects, it can calculate the isotopic intensities for you and compare the calculated isotopic envelope with the measured one. And that's also a score that you can exploit. How well does, according to the sequence that you have, fit the isotopic pattern that you measured to a calculated one? And that's what Skyline will always report as an I.P. So there are actually 3 .Ps in Skyline. I.P, R.P, and the normal .P. But that's just applicable to PRM or DIA data where you have high mass accuracy, high resolution. And then these here are the precursor ion scores. So if you have included an MS1 full scan in PRM or DIA, then you can look how well does a precursor here co-elute with your fragment ion chromatograms, and they should perfectly co-elute, not as shown here where they are not co-eluting. You can also look at the peak shape. Precursor MS1 peak shape should be the same as all your fragment ions. And you can look at the mass accuracy of the precursor. And you can also, again, look at these isotopic distributions of precursors and others. OK? Cool. So now just a few real-life examples, and then we are done. So this is data taken from myself, already many years old, where I just would like to show you some SRM data that I acquired in yeast. So this was my target peptide. I selected these 5 different transitions. It was a label-free experiment. It was non-scheduled, which you can see from the fact that I get data up to 45 minutes, which was my gradient length here. And in this specific case, for this protein, RPS6A, in these transitions, I got just one beautiful peak at 30.7 minutes. So this beautiful peak here has coelution, same peak shape, and is the most intense peak. So these first 3 criteria we had on the slide before are fulfilled, and I do not need any more information. I'm pretty sure this is my peptide, and I can keep on quantifying it. So in this case, it was easy to just use these 3 criteria that are easily available. But much more often, so RPS6A, I think, is one of the most abundant proteins in yeast, and that's why this data looks so beautiful. Much more often, data looks like this. So here's a new protein, RAS6 kinase. This was the target peptide, again, 5 different transitions. And now you can see that there were actually 2 retention times, namely at 16 and at 23 minutes, where I have coelution. Which of the two peaks is my target peptide? Skyline picked this guy here, but is Skyline right? What do you think? Look into the spectral library. So in other words, I don't have a spectral library. What do you think? I don't have a heavy peptide. Yeah, I don't have a database. Then what?
The internet's down.
The internet is down. So, I mean, you're completely right, because what I want to hear is, without additional knowledge, it would be it's impossible, very hard to say. It would be very risky to say it's this one or this one. I don't know. Just by looking at the first 3 criteria, which are easily available to me, it's not enough. I cannot tell. I cannot publish this. It would be too risky. So you need additional knowledge, and you heard it already, spectral library. So yes, I had a spectral library. This here was the MS2 spectrum. And Skyline also calculated for me the .p values. And you can see I got a .p of 0.99 for that guy and a .p of 0.82 for that guy. And that's now already pretty differentiating, right? So with this, I would say, actually, I'm pretty convinced it's this one. So the spectral library really helped me to differentiate between the two. Other example, SCH9. Other kinase, even more low abundant. This was the target peptide, only 4 transitions I could find for that peptide, and that's how the data looks like. I can already tell you there was a spectral library, and you see all the .p values for the different peaks. What's the right peak? So we have 0.99 for, I think, this guy, and this guy, and this guy. 0.93 for the big one. Yeah?
You have a proline in the sequence.
Mm-hmm.
So those are normally the most intense ones.
Yeah, but it's the Y1.
No,
There's another one. Yeah, could be a Y5. So, I mean, you see it here. This is the spectrum, right? There wasn't one transition that was crazy different in this case. So by just taking a spectral library as additional information, in that case, not enough. Peak is not good enough. What else can we do? Give up and go home and say, yeah?
then you would need the retention time, right?
Yes. So you could try to get the retention time information. Even though it might be, so yes, retention time information could help you to differentiate maybe this guy from that guy. But maybe still there are some close together and then retention time information. But retention time information would definitely be good. OK, we did it. It didn't help us. What else can we do? Heavy label standard, exactly. And that's also what I did in this case. I wasn't allowed to buy expensive heavy label peptide. But what I could do pretty easily at that time was to brew yeast 15N labeled. So just to do a 15N labeled yeast experiment. And so I generated the light as well as the 15N labeled yeast and mixed it 1-to-1. And here you see the corresponding spectra, how they look like. And now you must believe me because you don't see it very well. So this is the overlay of light and heavy. Light is red, blue is heavy. And there was just one retention time, which was here at 11.8 minutes, where I had perfect coelution between the red and the blue curve. That was this peak here. This peak is no longer as beautiful as the peaks you have seen before. But nevertheless, it's a peak where we have coelution, where we have a similar intensities of all the fragments. So the red is the highest. The others here are all similar. The .p was very good. Here you see the predicted retention time in the run was at 11 minutes. I'm at 11.8. So the combination of now all 6 criteria, coelution, peak shape, intensity, retention time, match to the library, .p, plus a heavy reference that is coeluting, helped me to find the right peak, even though it looked so horrible at the beginning. But you need to have all this additional information in order to dig this out of the data. And this is just the last example to show you that there are definitely also cases where you will target peptides and proteins with SRM and you will not detect anything. And it's actually also very important to define this threshold, or to say this is not detectable anymore, because guideline will very often pick you something and you must then decide, no, but actually this is not detectable, or this is just noise. It's sometimes more difficult than actually finding peaks. Okay, so are there any more questions? So this is just to give you a glimpse on how the data will look like that you will also work with in the next days, and you will very often have to go through these criteria that I just showed you and decide whether this is the correct peak or not. Yeah?
So if I generated some data from SRM,
So you mean that you will get slightly different retention times if you have acquired the data of different instruments and different setups? Yeah, that's absolutely. I mean, I wouldn't expect it to be a huge, if you apply a 60-minute gradient for both, you can easily see shifts of 5, 7, 10 minutes between LC setups, because there's just, yeah, it's a different setup, so that's not surprising at all. Also that you see maybe a different fragmentation pattern is something, because it's a different collision cell of the two instruments. So that's all possible. What I would compare, I mean, I still would think the retention time should be somewhat reasonable, and also the fragmentation should be somewhat similar, but not exactly the same. What for sure should be the same is the quantitation, right? So if you then quantify with PRM something or with SRM, I would expect that you see the same quantitation. And if you don't see that, that would be what would worry me.
yeah, well, I guess what I meant is like not comparing between machines, but sort of like I want to include both, whatever they detected, retention time, both in either machine. So if I've collected I just want to, cover all my bases.
But why would you want to combine them for one spectral light?
If the retention time is slightly different, or fragmentation, if one transition is better than in another machine than in this machine, so.
But usually, I mean, and that's what's usually the case, is that if you're staying on one instrument and one system, fragmentation is very reproducible and LC is very reproducible. So if you have information from one system, merging it with something else will, in my opinion, make it only worse. I wouldn't do that. That's what also people do, right? They make their instrument-specific libraries or instrument-specific assays. Okay? Okay, so then I've just a few take-home messages. So what I would like to remember you from this presentation is that targeted proteomics is an accurate and reproducible quantification, is optimal, or is the method for generating accurate and reproducible quantitative data. There is not just one data acquisition type in targeted proteomics. It's not just SRM or MRM, but also PRM, DDA, and DIA can be performed according to Tina's definition in a targeted way. SRM is definitely one of the most sensitive methods and can cover the largest dynamic quantification range, but it requires prior knowledge in form of these tables of peptide query parameters that you need to have in order to copy-paste them into the mass spectrometer. And these peptide query parameters are typically derived from spectral libraries that were generated based on DDA data. And if you want to identify peptides by SRM, there are these 6 criteria that we now discussed, which you can use in order to judge whether a peak is picked correctly and quantified correctly in an SRM experiment. And this looks also very similar in a PRM or DIA experiment. Yes, and at the end, I just would like to thank once more here the course organizers, Olga, Brendan, McLean, Mina, and Nat, for inviting me and all the upfront work that they did. I would also like to acknowledge a lot of former colleagues from the ETH in Zurich that helped generating a lot of these slides and discussions, and acknowledge also my new team in Munich. And thank you very much for your attention. Are there any more questions? No? You were asking lots of questions in between. I'm very proud of you. That's very good. Okay, so then I have another quick introduction into Skyline slides.